Alright, Assalamualaikum and good day everyone. Okay, this is the next question that you requested. Okay, I don't quite remember who requested for the discussion or solution. Okay, but if you read the question, it says that the emission spectrum of hydrogen in Lyman series is given as follows. Okay, the first information that you get from the stem of the question is, this spectrum is from Lyman series. Okay, and that should give you the clue that the final energy level in which electron drops to is n equals to 1. Yeah, n equals to 1. Okay, then it says, okay, these are the wave numbers, in micro per meter. In per micrometer. So this is 10.97 up until 8.22. And the first question is, calculate the minimum energy required to remove an electron from its ground state. Okay, minimum energy required to remove an electron. If you remember, this is the definition of ionization energy. And if electron is removed, starting from N1, because this is Lyman series, that means originally our electron is from N1. So our N1 is here, not here, but basically the lowest. Okay, so this is our energy level, N1. So our electron is originally from here. And if it is removed, that means the electron will be far away from the ground state. Which means if it is far away, it must be removed from N1 until N infinity. If you still remember, the way to sketch the energy levels are, the energy levels must first have a very long distance between each other, and then gradually the distance decreases every time until finally the lines meet. That means the difference is very, very small, that the lines actually, the energy levels actually combine, and that is n equals to infinity, which is also called the continuum. So E, this electron, is removed to N infinity. However, this is in terms of its energy level. We cannot calculate from these values, but we need to refer to the spectrum. Okay, if electron is removed, or the distance between N1 until N infinity, of course, will give you the largest difference in energy. Okay, and that is what we can actually identify from the given spectrum. Okay, as we can see here, the lines become closer to the left, which means the frequency increases in this direction. And if we relate frequency to the difference in energy, okay, I think you can recall by now that delta E equals to h nu, which is the frequency. If delta E is the largest, that is related to the highest frequency. So our line with the biggest energy difference, or that corresponds to the largest energy difference, must have the highest frequency, which is the line here. Yeah, this is the wave number. Yeah, for the difference in energy from N1 until N equals to infinity. It doesn't matter whether you know what is wave number or not. You can basically guess from the unit. If it is per micrometer, micro is just times 10 to the power of 6 per meter. That means wave number is just 1 over lambda. Yeah, 1 over wavelength. And you can solve for lambda here, in which the wave number is 10.97 times 10 to the power of 6, yeah, per meter. And that equals to 1 over lambda. And you can now calculate lambda, which is 1 over 10.97 times 10 to the power of 6 per meter. And you can calculate your lambda. And when you get your lambda value, you can basically calculate the energy needed to remove an electron from its ground state, that is the ionization energy, by using the formula of delta E equals to Hc over lambda, in which H is the Planck's constant and C is the speed of light. Alright, I think the rest you can continue. If you have further question, I will actually produce or record a continuation of this question. Okay, all the best.